My name is Otto, and I will be talking to you about extending Kubernetes the proper way, and in particular, I will focus on custom resource definition and controllers. So before we go into the interesting part, let me give a brief description of myself. So I am cloud native engineer. I'm working for a company called Container Solution, which I joined in November 2018. I have 6 years of professional experience as sysadmin, netadmin, developer, DevOps, and whatever else is in this area. I've been working with Kubernetes from version 1.2, which dates back to 2016, if I recall correctly. And I'm a huge fan of any cloud-native technology. So here is agenda for today's talk. So first, I will cover like multiple ways of extending Kubernetes. Then I will jump into controllers and operators and state what is the difference between those two. Then we'll cover custom resource definition, how they work, what's their purpose, and we'll end up by operators framework overview. Unfortunately, because of the problems with hardware, there won't be demo today, which is kind of sad, but whatever. So, extending Kubernetes. So Kubernetes is very pluggable platforms, and there are like multiple ways to extend it. So let me go through all of those ways. So the first one that I will speak to is about cloud providers. So cloud providers is an interface which allows the cloud providers to integrate Kubernetes directly with their infrastructure. So they are able, for example, to make services obtain IP addresses right away. So this is what all of the big cloud providers are using. So if you think, so the cloud providers which are using these are the biggest ones. So we may find in the Kubernetes repository the implementation of this, for example, for AWS, GCP, or Alibaba, or Azure, even Azure. I mean. Next one, extension point is kubelet plugins. So you may be familiar with this. They're like CNI, which is Container Network Interface, and CSI, which is not the TV show. It stands for Container Storage Interface. So those two plugins, they are in the form of the binary, and they allow us to provide networking or storage to the pods once they are scheduled on the node and scheduled and running on the nodes. Next one is kubectl plugins. So this is actually something new. I was not aware about this till like 6 months ago. So you can increase your kubectl user experience by installing dedicated plugins. So let me just show you quickly which one the interesting here. So you are definitely interested in the crew plugin. The crew plugin is like a package manager for those plugins. So it acts like a yum or apt-get on the Linux system. So you can like easily do the search for existing plugins and do the installation automatically, so it runs out of the box most of the time at least. Another one from this list, which is interesting, is the access matrix. If you have been working with Kubernetes previously, you may be aware that understanding the airbag roles for specific user may be kind of messy. So this plugins gives you like a good visualization what are the airbag rules for the specific user. This is something definitely useful. Another one, I should stand here because I'll explain. This is actually what was the previous talk was about. So another way to extend Kubernetes is through admission and mutating webhooks. So let me go through this diagram here, explain what's going on. So we, as a developer or the platform supporter, we can implement webhooks, which will be invoked by the API server on the different stage of request like cycle in the API server. So we have the API, can you see the pointer? Yeah. So we have the, still shaky. So we have the request, which is entering the API, the Kubernetes API server. Then once the request is multiplexed, it goes into next stage to the authentication and authorization. Once the authentication and authorization is done and the request is confirmed that it can enter the next stages, the request is is moved to the next stage, which is called the mutating admission. So if we configured our API server to support those mutating webhooks, the request is then forwarded to the webhook where we implemented our mutating logic or mutating processing. Once we are done with this processing of the request and of the resource within this request, the request is sent back to the API server, which continues with the processing of the request. So it does like schema validation, and then moves to the next one, to the validating admission. So it's the same thing as in the mutating admission. So if you define like a configuration for webhook validation, if we define like webhook for validating requests, the request is then forwarded to our webhook, and then the response, the result of this validation is returned to the API server, which then persists it in the etcd. So another one, this is not a common use case, and I'm not sure if everyone is aware of this, but you can actually write your own scheduler for the Kubernetes. I will not go into details, but this is something that it's good to know, that you are not like dependent on the Google scheduler from Kubernetes, and you can write your own logic how the pods should be placed on the nodes. So this is definitely interesting, but personally, I never met anyone implementing this. So just as a side note. Another important extension point in the Kubernetes is API servers. So we can implement our own API. So any request, so when the request enters the Kubernetes API server, then it hits the aggregated API, which forwards those requests to our API extension API. So it means that we implement our logic in completely separate logical unit. Like for example, this is for example the metrics server. So every time you are doing a kubectl top for nodes, pods, and resources, the requests are entering the API server. It goes through the aggregated server, aggregated unit in the API server. I will have another diagram so you'll be able to see better what's actually going on. So it enters the API server, aggregated server, and aggregated server forwards the request to our extension API, which then do the whole processing, the whole math to calculate the usage of the resources, the pod utilization, and stuff like this, and it returns response back to the client. So this is definitely one of the important way of extending Kubernetes. Another one is custom resources controller. So this is the one that we'll cover more in details in this talk, and this is definitely a major one. There's a lot of interest in this currently. So what custom resource controllers are following the operator pattern, which I will speak later. But the main idea behind this is that the controllers are making changes to the Kubernetes cluster or to the application based on the custom resources. I will speak about this later on the next slides. So here we have like a summary of those techniques of extending Kubernetes, which I just showed you. So we have like a webhook backend. So this pattern applies to the admission webhooks or to the API extension pattern. Another one is the binary, extending Kubernetes through the binary plugin. So this is the case for the CNI and CSI. So kubelet is invoking those binary plugins during the deployment of the pod on the node. And another one, this is which we are interested in, is the through controller. So controller is watching the resources in the Kubernetes and makes changes based on the resources in the cluster. So here is a short summary of the extension that I showed you with a short sentence of purpose. I will not go through it right now. I will share my presentation later, so if you don't want to go through all the slides, you can just stick to this one and read what's there. So let me go to the core topic of my presentation, which is controllers and operators. So controllers and operators, well, it's all the same. There is not much difference. This is just the notions, but their purpose is kind of the same. They are using like and they're implementing the main core pattern, so which means the control loop. So control loop in Kubernetes, the main idea is that it watches the shared state of the cluster in the API server and makes changes attempting to move the current state toward the desired one. So here is a small diagram which represents this. So this is a user, so this is who we are, and we are manipulating resources in the Kubernetes cluster. So we have a controller which is watching those resources and is getting a notification about any changes for these resources. Once the notification is received by the controller, it performs some operation on the external system in order to make the external system follow the desired state. In addition to this, controller is also responsible for error handling and reconciling the whole system every specific interval of time. Another way of calling it is the reconciliation. So this is the same. So the controller keeps underlying objects in sync with Kubernetes API. So we can like differentiate two types of reconciliation. We have unidirectional and bidirectional. Unidirectional means that our controller is watching only the resources and they make changes to the external system. Bidirectional means that our controller is watching actually both ways. So it watches the resources that we are creating and also the external system. And it ensures that the external systems are in sync with what we have in the resources. And the important part that we have to keep in mind when we are developing our own operators and controller is that the reconciliation must happen at the startup, so the controller is aware what is the current state of the system. Otherwise, it may lead to some corruption of the state in the controller memory. It may lead to bad things. So you may ask yourself, okay, this guy is talking about this control loop, but is it actually implemented anywhere in the core Kubernetes? Is it used anywhere? So yes, it's actually like the core pattern for the Kubernetes, the main logic behind it. So let's go through this example. So we are a user, and we are using kubectl to create a deployment. It's small, but I think you will be all right. So user is creating the deployment with kubectl. The deployment then is placed in the API server. So once it's placed in the API server, the controller manager, and in particular the deployment controller from controller manager, is receiving an event over watch channel. So once the deployment controller receives an event that the deployment was created, it starts to create replica sets according to the instruction determined in the deployment definition. So once the replica set is created, another event is generated to the controller manager, but this time this event its destination is replica set controller. So replica set controller starts to create pods based on the information from the replica set resource. Once the pods are created, then yet another event is generated, but this time for the scheduler. So the scheduler receives information that the new pod was created in the Kubernetes cluster. So it receives event and it starts calculating what is the best node for this specific pod. Once the node was calculated, it updates the pod with the node information. Once the pod receives a node information, another controller, this time kubelet, receives an event notification that this pod is ready to be placed on this specific node where the kubelet is running. And the kubelet does the rest of the stuff. So it communicates with container engine over a socket, which then container engine creates containers. Okay, so let me just get to the point. So I presented to you this whole controller pattern and control loops, but what is their actual purpose? So before we go into their actual purpose, let me just clarify the dictionary definition of operators. So dictionary definition of operators, that there are controllers with some operational logic. So not much difference between operators and controllers, as I mentioned before. So operators, their main purpose is it's a method of packaging, deploying, and managing Kubernetes application. It provides also automated way of provisioning user resources, configurations in the Kubernetes cluster. So we can have like as a users or as a operators of, as a administrator of the Kubernetes, we have like a consistent setup across multiple environments. So let me give you an example. So imagine that we are an organization and we have like multiple teams within the organization, and each team has a dedicated namespace in the Kubernetes clusters, and each of these teams requires a database instance. So what we do then, we just create resources for each of those namespaces, and the operator takes care of creating the databases in each of those namespaces with the dedicated configuration, which was specified in this dedicated resource. So there are like multiple examples of the operators. So we may have like Postgres operator, Prometheus, Jenkins, Consul. Actually, now there is a lot of, as I said before, there's a lot of interest in this pattern. So whatever application you can come up with, there is probably an operator being developed right now. I will show you later to prove this point. But before we go to the how to build actually operators, let me just give you a quick overview what are custom resource definitions. So custom resource definition are, but before we go into custom resource definition, a little bit lesson of history. So before CRDs, they were TPRs, which called third-party resources, and they appeared for the first time in the Kubernetes version 1.2. They used the core API server for handling TPR requests. This was like the big limitation for this because it was breaking like the backward compatibility. By the core API server means the TPRs were using the same, let's call it processing unit as pod, services, and any other standard resources. So it was a big limitation. Another limitation was that they supported only namespace objects. So because of those limitations, they were removed from the Kubernetes in version 1.8. So from the version 1.7, the custom resource definition was introduced. So as you may see here, there is like a dedicated processing unit, which is called API extension, just for those CRDs. So thanks to moving this CRD, thanks to moving the TPR processing from the core API server to the API extension, we are not like, we have like, there's like a bigger flexibility in developing new features or to maintaining code. So this was the main reason for moving from TPRs to the custom resources. So yeah. So what is the purpose of CRDs? So they allow you to define Kubernetes style API as add-on. So you can have, by defining CRD, you are getting an endpoint which supports the CRUD operation, so create, read, update, and delete. So API server handles the entire lifecycle of those CREs as well. And we are getting also like dynamic registration in the Kubernetes API. And the important thing is that by creating CRD and the custom resources which are attached to it, we are able to manage them through the kubectl. So what are the benefits of using those? So they do not require programming. Well, this is an overstatement because they do require programming, but you have like a freedom to choose language of your favorite programming language for creating CRD controllers. There is no additional services is required to run and manage custom resources because it's all handled by API server. And for the same reason, because CRDs are registered in the Kubernetes API server, we are getting the simplified API versioning because it comes with the Kubernetes. And since CRD endpoints are part of the Kubernetes API server, no user maintenance is required, and we are getting like a lot of additional features just by using the API server. Like, for example, we don't need to implement HTTPS because it's done by the Kubernetes. Well, the discovery mechanisms are there. The watches and listing are supported also out of the box. So there's like a lot of benefits by using those. So now, once we know what are the custom resource definition, we may start building our own operator, and it's going to be easier than you think. But before we go to the easy part, let's start me with a little bit history. In the dark times of 2017, the main pattern, or the main design guide for building operators were the sample controller, which you may find in the Kubernetes repository. So this sample controller was containing all the best practices that should be applied, that you should keep in mind while building your own operator. So it was mostly using the standard client Go for building, and sorry, it was using like standard client Go. Before I deep dive into this picture and explain what's actually going on here, let me define a few notions for you. So we have a reflector. This is the structure in the client Go, which is watching the resources in the Kubernetes API server and reflects those objects in the queue. We have a Delta FIFO, which is a queue, producer-consumer queue, where a reflector is intended to be the producer, and the consumer is whatever calls the pop method. So the consumer here is the informer, and the role of informer is to sync events from the FIFO queue to the downstream store. It is cache in our case, and also it invokes the event hooks. Indexer is just a method which is placing the objects in the cache, and event handler is then interface which calls the user implemented functions based on the different event action types. So let me get into details here. So reflector is receiving notification from the Kubernetes API server. Then it adds the object to the Delta FIFO queue, which is then popped by informer. So informer, what it does, it puts the object into the cache, and it invokes the event handler. So event handler was supposed to process 3 types of actions. So it was like addition, update, and deletion of the resource. So we as developer, we had to implement those methods. In addition to this, we were responsible for implementing any additional work queue that we needed, error handling, or requeuing strategy. So developer was responsible for implementing everything. Luckily for us, there is no longer need to do this, because there is like a bunch of Golang bunch of operator frameworks that we may use to actually generate the whole code for us. So from the Golang, we have the operator-sdk and kubebuilder. From metacontroller types, we have like metacontroller and KUDO. And there are as well like operators for other languages, like a Java operator-sdk, abstract operator for Java, or COPF from Zalando, which is a Python operator framework. The thing that we have to keep in mind that those operators for other languages are kind of limited, because the Golang operators are actually reusing the Kubernetes libraries from the mainstream, so they're always up to date. But this one, it really depends on the developers who are leading the project, if they are like reflecting the most recent changes to the Kubernetes. So this is why I always suggest to build operators in the Golang. So yeah, this is like the new way of building the operators. So there was like controller runtime library which was created. So it makes easier our life as developers. So we are just we are just only responsible for implementing the reconciliation logic. We don't have to bother with implementing error handling, work queue, or other requeuing strategies. So let me go through here what's actually going on. So in the previous slide, you saw that you had to implement like 3 different methods, functions for it. So now those 3 objects and functions are flattened into single object key. This object key is like a single structure with only 2 fields, like namespace and name. So then the object is placed into our work queue. There is some additional processing done, which I'm not going to cover into details. And then the object is passed to the reconciliation logic. So this is where we, as developers, we are developing the logics. We are ensuring that the actions performed on the on the Kubernetes cluster are correct. In addition to this, the controller frameworks are giving bunch of very useful tools or interfaces. So we have like an easy way to get objects directly from cache this time. So it was not possible in the client Go. Well, it was possible, but it required some more work because here it is given to us out of the box, which is very nice. So where can this approach be found? So yeah, it can be found in both of the Golang operators. So it can be found in the kubebuilder from Google one and operator-sdk from Red Hat or IBM, as there are nowadays. So let me give you a few more details about each of those. So operator-sdk gives you also like a way to create your operators by using Ansible on Helm, if you are not familiar with the Golang. It includes like integration with the operator lifecycle manager, which I will give you later. It has like the operator-sdk CLI includes like a scorecard subcommand, so you can actually assess if your operator is following the best practices. And it has also like E2E testing framework, so you can test your operator against actually running real-life cluster. So since the Red Hat is behind operator SDK, there's like already the whole ecosystem created around this. So we have this operator lifecycle manager, which I mentioned before. So this operator lifecycle manager allows you to easily do the versioning of your operator. There is also like operator metering service, so you can get nice usage reports for your operators. So this is very nice. Another thing, if not the most important out of it, is that Red Hat created operator-hub.io, which is like a repository for all the operators that are created by the community. So before you deep dive into developing your own operator, it is always worth to check if there is no one existing already. So before developing stuff, just ensure that it does not exist. So kubebuilder is another framework which is generating code for us. This one is from Google. The interesting part about kubebuilder is that it is part of the Kubernetes SIGs. So you may find this in the Kubernetes organization on the GitHub. And few core points about this one. It includes env-test package, which allows operator developers to run tests against standalone API server and etcd. It uses Makefile to assist in the operator tasks like building, installing, deploying to the cluster. It uses Kustomize instead of the standard manifest for deploying the operator and the custom resources managed by this operator. And it has like a better improved support for admission and custom resource conversion webhooks. So for example, if our CRD has like multiple versions, then the kubebuilder is the one which is supporting this at the moment. The operator SDK is still lacking this support. So this was it about the standard Golang operators. And another family of operators are metacontrollers. Well, this is the name that I applied to them, and I will show you why. Well, I will not show you why I'm calling those metacontrollers, but whatever. So the main idea behind metacontrollers is that the whole reconciliation logic is moved to the external components. And those components may be a webhook written in any programming language of our choice, or just as simple as a YAML definition with the recipe what should be done. So there are like two controllers which are following this pattern. So we have like a metacontroller from Google. So let me explain how it works. It's very similar for the next one as well. So first what we do, we have a metacontroller running in our cluster. We are configuring this through the decorator or composite controller resource. Once it is configured to list and watch our defined resources, and with the whenever a new user-defined resources, in this case our custom resources, is created, it communicates with our webhook. So it sends requests to the webhook, and we as developer, we implemented our logic for processing those requests, and we define what has to happen in the cluster based on the information provided in this resource. So once we did all the processing, the response is returned to the metacontroller, and metacontroller performs all the actions on the API on the Kubernetes cluster. So as I mentioned before, the major the positive point about this is that this webhook may be implemented in any language of your choice. Another operator from operator framework from this family is KUDO, Kubernetes Universal Declarative Operator from Mesos, or whatever they are called nowadays. I think they changed name. So this is like a universal controller that can be configured with a declarative YAML manifest to manage the workloads. And we can have like one KUDO controller to manage like multiple workloads, so which gives us like a consistent user experience in the which gives us just a simple and consistent user experience if we are like running multiple workloads per cluster. And it also encourages reuse of existing operation tools like MySQL dump, and we can plan the actual usage, how this operation tool should be used by just sequencing the usage in the YAML files. And some final thoughts. Yeah. Well, here is like a summary of what I said. So in my opinion, if you want to create your own operator, you should go for Golang, because this is like obvious choice, and the Golang libraries are always up to date with the Kubernetes one. The other important thing in creating operator is to try to not reinvent the wheel, but use existing one instead. So this is what where I showed this operator hub.io. Check if the one is existing. If you need to build your own operator, you may think about using metacontrollers for prototyping. So if you are not familiar with Golang, before jumping into developing Golang operators, you may use metacontrollers and develop the logic in your favorite language. And another important thing is that do not try to automate your Kubernetes cluster other way, because it won't work. I saw people trying to build automation with some magic bash scripts, magic config management, but it's really like the controllers and operators framework is like the way to go with the Kubernetes. So this is it from my presentation. Any questions?
Yeah, exactly. Any question? Yeah, I have a question. Why there's no bash implementation of operator-sdk or something like that? But just rhetorical.
Okay. Feel free to create one.
There is. Okay. Yeah, but thank you for that. That was very interesting. Yeah, and guys, do you have any questions to Adam?
I have a question about extending API server by custom one. When you will want to use that instead of writing operator?
First of all, if you, for example, if you don't have a need for the for using kubectl with the resources managed by this custom API extension server, then you don't have, it may be interesting for you to write your own. Another thing is that those CRDs and the endpoints created by those CRDs, they are following like the Kubernetes specification, which is like namespace, the name of the object, and then the names, well, the kind of the object, the name of the object, and things. So if you have like very specific use case which does not follow this requirement, then you have no choice. You have to write your own API server for it.
I have a question. If you're using a managed Kubernetes service, how many of these mechanisms would be available usually? Like if you're on
you mean from the extension points or operators?
Operators.
Because if you're running like GCP managed Kubernetes, there is no limitation in using operators, because the only thing that Google is hiding for you is the control plane, but you may run operator in your own namespace. So you may just give a proper airbag to this operator service account, and it will be able to do anything. So there is no limitation. But if you ask of other extension points, so there, of course, you won't be able to use all of them in the managed Kubernetes.